Here's another example of sort of an angular collision. Merry-go-round, which is just a spinning playground toy, and we can approximate it to be a disc. Merry-go-round with mass 112 kilograms, and radius 1.2 meters, is spinning at 3.50 radians per second in the upward direction. Upward, meaning it's going around and around, so our angular velocity is up. When a girl with mass 38 kilograms leaps onto the eastern edge with a velocity of 3.81 meters per second at west by 67 degrees north, determine the angular velocity of the girl in the merry-go-round after she lands. Okay, so here's what's going on. We've got our merry-go-round. It's spinning. Upward direction is its angular momentum. 3.50 radians per second. Girl leaps onto the eastern edge, so she's landing right here, and she has a velocity 3.81 meters per second at west by 67 degrees north. That's over here. And we're given the masses as well. So keep in mind, our angular momentum was angular momentum was the linear momentum times r times sine theta, where the theta was the angle between these two. So the initial angular momentum of the girl is her mass times her velocity times her radius. I said the thing has a radius of 1.2 meters, times the sine of, well, the radius is in this direction, their velocity is in this direction, so it's just 67 degrees. Alright, so, and momentum is conserved here. There are no net external forces acting on, net external torques, I should say, acting on the merry-go-round and girl. So we could say that our initial angular momentum equals our final angular momentum. Our initial angular momentum is the initial angular momentum of the merry-go-round, which is a disk, which is I 1/2 mass 112 r squared times omega, which is 3.5. And the girl's angular momentum is the same direction as this. If this was spinning the other way, they would have opposite signs. You can tell she's kind of rotating in the same direction, as it were. Plus, I don't want to write this again, all this stuff equals our final angular momentum, which is the moment of inertia of the disk plus the moment of inertia of the girl, which is a point. We can consider her to be a point mass, so she is m/r squared times their omega final, and so we can calculate what that comes out to be. Generally speaking, any person or dog or any sort of object that shows up on top of something else is going to be considered to be a point mass, which isn't entirely true, but as long as the radius of the width of the person or dog or whatever it is substantially less than the radius of the object in question, then we can treat it as a point mass without too much inaccuracy. This thing is 1.2 meter radius, and people generally aren't that big across. Especially little girls with masses of only 38 kilograms. Anyway, so the omega final comes out to 3.2665, etc. radians per second. again, that's another situation where momentum is conserved, and we can use conservation of momentum to solve problems. Now, the reason that we were able to use conservation of momentum was because we said the net external torque was 0. If the net external torque is not 0, then we wind up with the equivalent of the impulse momentum theorem, which is just that a torque times time would be equal to an I delta omega. So we could have if we had a net torque on the system, then we would have to utilize this equation. Likewise, we can also have work in the rotational sense. Remember, our equation for work was F cos theta times D equals work, which is equal to a delta KE. The work done was a change in kinetic energy. With torque, generally speaking, you can only really apply a torque in the direction the object is already rotating, because rotating objects are usually anchored. So most of the time this theta will go away, but it could show up there. But it's gone off enough that we can write the equivalent equation, tau delta theta is equal to a delta KE rotational. And this would be linear or translational. Usually I'll write translational. They mean the same thing. And this would be just like with our force and work, the change in kinetic energy is negative if the torque and the angular displacement are in opposite directions. So that's another rotational thing that is exactly like its linear equivalent.